Hi, this mini lecture is going to cover the Fourier transform. You've probably looked at or seen or learned about the Fourier transform in some of your other classes if you're in science or engineering. And I'm not going to go into a mathematical derivation of the Fourier transform. What I'm really interested in explaining here is why and how does the Fourier transform actually work. So let's, before we get into the details of it and the mechanism, do a little bit of review. The Fourier transform, as you probably remember, changes something. And this can be basically a signal. Let's just put a scribble in there for something. It can be a signal, it can be a wave function, it can be a voltage, it can even be something like financial data. But it changes whatever signal or data you have from the time domain to the frequency domain. And of course you can change it back again through what's called the inverse Fourier transform, which is just the Fourier transform again. And the really key words we have to understand before we go further are what we mean by time domain and what we mean by frequency domain. So let's take a look at time domain and frequency domain and some assumptions inherent to this. Here's a signal in the time domain. We're going to call it f of t. I'm going to use f of t throughout this for our signal in the time domain. And I've just driven or drawn a random line here for this signal. One way we can represent this signal instead of a continuous function is as a sum of numbers that occur at each point in time. And let's take a look at an example of this. The value of the function f of t at time t1 here is the number f of t1 at this particular time, or the delta function of t minus t1. In order to create an entire signal rather than just having a number at some point in time, we essentially define f at point t2, f at point t3, f at point t4, and so on and so forth, where this delta function assures that we're at one particular point in time. And so another way to represent this signal is essentially by the sum of the numbers that occur at each point in time multiplied by the delta function at each point in time. And of course, being in engineering and mathematics, we recognize that we don't always do sums. We let the delta function go to 0, the spacing tn of the different points tn approach 0, and so we really do this particular type of integral. And you may recognize this as a convolution with a delta function, which just returns f of t. And that's one way we represent signals in the time domain. And we don't usually go through this formalism, but we do recognize that any signal in the time domain is a sum of numbers, the amplitude of that signal, at discrete points in time. And we sum up all the points in time and we get our signal f of t. So let's remember that as we go forward. Of course, there are other ways to represent signals in the time domain f of t. Instead of summing up points at each point in time, we can sum up functions that cover all time. And functions that cover all time are essentially waves. And remember, we describe a wave or a sinusoid as the magnitude of it with an exponential term, and we can represent that through Euler's equation as essentially a real part that is the cosine, as well as an imaginary part that's proportional to the sine. And the cosine has amplitude A, and the sine part has amplitude B for the real and imaginary parts respectively. So how does this work? Well, here we've drawn a cosine wave in green, the real part, and a sine wave in red, the imaginary part, that are at some frequency, omega 1, with amplitudes A1 and B1. And we take those particular sine waves, and then we sum up sine waves at the next frequency, omega 2, that have different amplitudes, A2 and B2. And we keep going on and summing up these sine waves over and over and over and over again. So here's another sine wave that happens to be at a higher frequency, omega 3, with again different amplitudes. And if we sum up all possible combinations of sine waves that have the right amplitudes, we can reproduce this function, f of t, no matter what f of t is. And so that's another way we can create a function, not by summing up values at points in time, but by sine waves that stretch over all time that have the right amplitudes, as long as those sine waves have real and imaginary parts. So what does this thing look like? And And before we go on there, let's recognize that any time domain signal can be represented as a sum of sine waves. You've got to accept that to go forward. What do these things look like in the frequency domain? Well, what we've got here is our function f of t, and I've drawn two sine waves. The real part, the cosine term in green, the imaginary part, the sine term in red. We can represent these two waves by this generic function, with our amplitude a sub n for the real part, b sub n for the imaginary part, both occurring at frequency omega sub n. And it's really hard if I were to overlay a bunch of these sine waves on top of one another. This graph would look like a complete mess and you couldn't see anything. So essentially the way we represent a function that's a sum of sine waves is not in the time domain. We don't put all these waves on top of one another. We simply plot the amplitude of the cosine term, or the real part, and the sine term, the imaginary part, as a function of omega. And this now is what we mean by representing a signal in the frequency domain. You can see that for this particular sine wave, omega sub n, the cosine term is somewhat larger than the sine term. They both have positive amplitudes because the phase is defined correctly. And you can see at this particular frequency, omega n, right here, where that value is omega n, here's the value of our sine, and here's the value of our real part, our cosine function. And if we define the amplitudes of these two sine wave components, in other words, the amplitude, or the size of the function b sub n for all frequency, the imaginary part, and the real part, a sub n over all frequency, this frequency domain representation, f of omega, is what we get when we do a Fourier transform. We convert a signal, f of t, from the time domain over here into the frequency domain over here through the Fourier transform. Essentially what we're going to get is a real and imaginary term for f of omega defined at all frequencies that say how big the amplitude of the sine wave is that needs to make that function f of t for all frequencies. Whew, okay. So, to review, the important thing is a frequency domain representation. A frequency domain representation gives the amplitude of the real and imaginary parts of the sinusoids that you have to sum together to give the time domain signal at each frequency. So keep that in your head as we move forward.